Everybody, this is a narration of the Uninformed Search slides. So let's see what we can do. The key takeaway of this presentation is that for you to realize that the search algorithms that we're going to be discussing today and next time, they all use the same core algorithm. The algorithm is pretty much the same. They differ primarily by the data structure that we use. And so we'll be using queues, stacks, and priority queues. So let's see what we can do. So let's start with having a look at search trees. So let's do some tree appreciation. After all, I created it, right? So it's a pretty abstract tree, but that's okay. So the idea is we can go from state A to B, C, or D. From D, we can go to H and I. From C, we can go to G. From G to N and O. Okay, so and that's really all we need to understand the search procedures that we're going to be looking at. So we're going to start with breadth first search. So in breadth first search, which is one of the algorithms that I asked you to implement for the search assignment, we start with the root, which is our start state, and then we're going to produce. We're going to look at its children next. And then we're going to look at its grandchildren over here, and then the great-grandchildren. So in breadth first search, maybe a better name would be level order search. So we start with the root, then all the children, all the grandchildren, and so on and so forth. So that's how that one works. So let's have a look at an algorithm over here. So what we're going to be using for breadth first search ends up being a queue. So let's see how we can understand that. So what we're going to do is we're going to place the root on the queue, in this case A, and then we enter a loop. So in this loop, we dequeue, we call dequeue in our queue, and that obviously removes element A from the front of the queue. Next thing is we're going to see whether the goal is satisfied. If it is, we'll terminate. Okay, and typically we return some sort of solution, a path from the root. Sometimes, that is stored somewhere else, and some other procedure knows where to get that information. But if not, we produce all the element successors like B, C, and D, and we add them to the queue. Okay, typically in this presentation, first B, then C, then D. But remember, we removed A from the front of the queue, so B now will be the first element. But as it turns out, that's not quite right. So let's sort of understand what the problem might be. So we're actually going to scratch step 2D. So why? So suppose we're at node B, and at some point in time we generate its successors, and they're E and F. But what this abstract notation hides is that E might be the same as A. We have seen that in the prior presentation. So in which case we have engaged in a cycle, right? We go from A to B to A by A, B, E. And typically that's not something we're interested in. And so we want to eliminate those situations. So what we're going to do is, for each of the successors of A, we first check whether we have seen them before. Okay? So we check whether it's already on the queue. So we produce the element successors, but before we put them onto the queue, we check, have we seen this thing before? In other words, is it in the queue? And if it's in the queue, we don't add it again. Well, as it turns out, this again doesn't quite solve the situation or the problem that we're trying to eliminate. So even the one that we talked about, ABE, notice that we'll pop A off the queue, or we dequeue it, right? So it's not on the queue anymore. So if we then check, hey, have we seen E before, we wouldn't know about that, right? So as it turns out, this step that was intended to eliminate these sorts of cycles really doesn't eliminate necessarily cycles. What it does eliminate is, suppose F is the same as D or H or G or one of those things. So cousins, right? If we have, if F is already somewhere on the queue, then since it's a level order search, it can be found much faster. So if F and D are the same, we prefer to explore D next and not put F on the queue, because we got to D in one step and to F took 2 steps. So what we need then is we need another data structure. So the type of the data structure doesn't matter. A linked list will just be fine. So that's what we're going to do next. So we're going to add another data structure. Let's modify our algorithm. So somewhere over here, we initialize this linked list called closed. So what we're going to do is when we dequeue the first element, or whenever we dequeue an element from the queue, we place that element on the list called closed. We then check whether the goal is satisfied. If yes, again, we terminate. Otherwise, we reduce all the successors. And now for each successor, we check two things. Is it already in the queue? If so, we do not add it again. And we check, is it enclosed? If it's enclosed, this new data structure that captures those that we have already explored, like A, and then once we're done with we explored B, we knock it off the queue, we add that one to that closed list. Again, we do not add. And so in all other cases, yes, we add the successor to the end of the queue. And it's very important that you do that because this does miracles in terms of improving the efficiency of any of those search methods. We don't want to go through cycles. That just makes it very, very inefficient. All right, so let's see. So that's what you need to understand. You need to understand this basic algorithm. So if you don't understand it, go back or ask me some questions. It's very important that you're comfortable with that. So let's have a look at depth-first search. As a matter of fact, we won't really look at it in any detail because you already know about it from backtracking, right? So rather than level order traversal, we sort of like drill deep, okay? So what we're going to do over here is we might go from A to C or B, C, D, and then we pop this one off, and we look at E and F, we pop this one off, we look at K. So we're just going to go down, okay? Now, it's the same behavior, it's the same algorithm. The only difference is that we're going to use a stack. So we push, say, DCB on the stack, and then next time around we do pop, so we get B. Then we put F and E on the stack, so we now have D, C, F, and E on the stack, so we pop E off, and then we put K on the stack, right? So we have D, C, F, and K. That's it. All right, let's move on a little bit. And so uniform cost search is not the most exciting algorithm you can ever think about or implement. However, it adds a very crucial component that is very, very helpful, and it's a stepping stone to what we call is informed or heuristic search. So far the cost of going from one node to its child was not specified. In games, typically, we count the number of turns, and sometimes we collate those in statistics. So if it's just a game, we sort of may say up step, just the cost of 1. So all of these arrows have a cost of 1. But there are applications where there are different costs between neighboring nodes. So think about navigation software, right? So navigation software, there might be different costs associated with each of these edges. So now what we want to do is we might take advantage of that. So if we have navigation software, we might want to find the least cost, right? So in this case, we again start with A, and we produce all its children, B, C, and D, and so we'll put them on a data structure, and we want to pick the least one, right? We want to pick this one over here, least cost, and so that's what we would do. And then over here, we would produce its children, and so then the cost of H would be 2, 1 plus 1, right? Of I, 3, of J, 5. And so we then have a choice between exploring this node and that node, right? So, but the key thing is the only difference between uniform cost search and breadth first and depth first is a data structure. So now we're going to use a priority queue instead of a queue or a stack. So again, uniform cost search is a stepping stone, but not the most exciting thing you could ever do. So here's an example, right? So I looked at Google, I Googled Rose Holman, and then I zoomed out a little bit. So suppose you plan a trip somewhere. So The measure of the trip, sometimes it's time, sometimes it's miles. We know they're sort of roughly correlated. Not if you drive in New York City or in the East a lot or around Chicago. It's a little bit different. But so let's assume we want to save on gas, so we take the least distance. And so that will be the metric for our cost. And so what we have over here, this might be the distance between two neighboring cities. And so that's the metric that we're going to use now. But the drawback of uniform cost search is that it doesn't have a sense of direction. So suppose you want to plan a trip from here to somewhere down here in Daytona Beach, right? And so, yeah, you first explore, roughly cities in this neighborhood, and then in this circle, and then this circle, and this circle. I mean, again, you just sort of consider the cost, and the cost to go from here to Atlanta is about the same as to go from here to somewhere in Wisconsin. That might be Eau Claire, actually. So it really doesn't help you in that regard, but it introduces a key concept, which is that of a cost function. And we're going to go back to that in the next slide presentation. But before we do that, I want to sort of like show you something from a book, a key book on AI called the Russell and Norvig, or IMA, or AI, a Modern Approach. So here's an imaginative way of reducing the search space, because the thing that really kills us is that these search spaces typically are exponential. So if a branching factor of 2 and the solution is at n, well, 2 to the n, right? How much can your computer do? Well, typically it sort of like peters out at n equals 40, right? We can't really do much more than that. Big deal if it's 50, right? You're probably going to go through more than 50 cities on the way to Florida. So why don't we sort of like do something that we sometimes do in math when we give proofs? We start from the start state and we work backwards from the goal state too. And once we have one path that meets, great, we have found a good path and probably a shortest path. And so the question now is, how much does it improve the efficiency? So again, if we have a branching factor of 2 and the solution length is known to us to be n, then ordinarily it would be 2 to the power of n, right, to get from start to goal. But it's different here, right, because they're going to meet in the middle. So what's half the path length is n over 2, right? So we have 2 to the n over 2 plus 2 to the n over 2, which is 2 times 2 to the n over 2, which is what? 2 to the n over 2 plus 1. And that is significant. So suddenly, if your computer could only solve problems of n equal to 40, now we can get pretty close to n equal to 80. So we can almost double the solution length, right? It's not as easy as that, because whenever you generate new nodes, you kind of have to say, hey, does this one show up anywhere over here? So you have some additional costs. But by and large, this is a huge improvement, right? Just so like by doing 2 searches, forwards and backwards. Alrighty, folks, that's it for this slide presentation. I'll see you later. Bye.